Hey, good morning, everybody. This is Mr. Ainsworth, and we're getting into our last lesson on how to find a Hamilton circuit using what's called the cheapest link algorithm. Okay, this is the fourth out of, well, fourth four algorithms looking at traveling salesman problems. Okay, and this one here, it kind of looks like the nearest neighbor, but it's different. Okay, we call this the cheapest link algorithm. Okay, so here we go. Our goal is to find a Hamilton circuit by choosing edges that have the smallest weight, okay? Or if it's a cost, the cheapest, okay? That's why it's called the cheapest link algorithm, because sometimes these weights represent costs. In real life, that's the case many times. So what we're going to do is we're going to pick the edge with the smallest weight first, okay? Anywhere on the graph. Okay, so you can see, you can think of it as the smallest weight, the least weight, or the cheapest. All right, we're going to highlight them. So get out your red pens or your highlighters, and we're going to highlight the edges as we select them. The key thing is on this one, though, I don't care how you write your circuit in the end. When we pick the smallest weight first, I want you to realize that we want to pick the smallest weight anywhere in the graph. Okay, and then what we're going to do is we're going to pick the next cheapest edge or the smallest weight anywhere in the graph. So the key word here that I'm going to underline here is anywhere in the graph. And we're going to keep on doing this unless two things happen, okay? And this is really, really important because we have two conditions that need to be met as we do this selection process. First of all, when adding an edge, if it creates a circuit early, all right, not containing all the vertices, all right, which is required by a Hamilton circuit, all right, we cannot add that edge or we cannot select that edge. All right, so we don't want to create a circuit early, okay? That's a no-no, okay? These have to be met, these conditions. All right, secondly, adding an edge would give a vertex of degree 3. That's also a no-no too, and you got to think about that when you look or when you analyze or find a Hamilton circuit. You got to be thinking of the degree of each vertex, because a Hamilton circuit. Let's make a little note here. You must visit every vertex exactly once, right? Visit every. That's keyword vertex exactly once, which has a big implication here. Because of that, let me just draw a quick little circuit here. Let's suppose this is our circuit. Okay, these big dots right here, the vertices, okay? And if you take a look at any vertex, and I'm talking about these right here in red, the vertices, you'll notice that each one is degree 2. All right, that's degree 2, degree 2, degree 2, degree 2, degree 2 for any Hamilton circuit. And it's because each one's visited only once, not more than once. So you either have to enter it and then exit. Okay, you enter the vertex and then leave it. All right, degree 2. Or reverse that, you come into it or you leave it. Let's say you leave this one. You leave this one and then you come back into it the other way, finishing the circuit. So I don't care how the Hamilton circuit looks like. All right, every Hamilton circuit, because of by definition that you hit every vertex or you meet every vertex or visit every vertex exactly once, they all have to be degree 2. Not true in an Euler circuit. Some of the vertices have to could be higher degree. All right, but in a Hamilton circuit, they have to be degree 2. So we do not want degree 3 vertices. So if we select an edge creating degree 3, that'd be a bad idea. Okay, so that's we cannot do that. So we would not select one that would create a degree higher than 2. So we don't want circuits early, okay, and we don't want degree 3 vertices. Remember that. And then we keep on selecting the cheapest, the next cheapest, or the next smallest weight until we form the Hamilton circuit. And then after we do, find the circuit here. When we're done, we're going to provide the total weight, and we're going to write the Hamilton circuit ordering at the starting vertex in the problem, whatever it's asked for. Okay, so we're going to obviously do this, find the total weight, figure out, what the total cost would be if it's a cost problem. And then we're going to write the circuit in terms of a starting vertex, whatever it may be. So let's get started here. So our first example is a simple one. We got a complete graph, K5, and we want to find a Hamilton circuit using the cheapest link algorithm, okay? Not nearest neighbor, okay, not brute force. or a repetitive nearest neighbor or anything like that. We're going to go cheapest link. Okay, and then when we're done, we're going to write the results starting at A when we're done. Okay, so the first thing I'm going to do is I'm going to list the weights. Okay, list all the weights. All right, in the diagram, starting with from least to the greatest, from smallest to largest. Okay, so I see 2. Okay, 2, 3, 4, 5. So 2, 3, 4, 5. All right, there's no 6. All right, there's a 7 and 8 and 9, 10, 11. So 7, 8, 9, 10, and 11. So from smallest, all right, to largest. And the reason why we're going to do that is because you always start with the smallest or least weight. Okay? Okay. So what we're going to do is we're going to highlight as we go. It's always easier as you do this. Okay? Highlight as you select edges. All right, so what I'm going to do is I'm going to start with this one here, and I'm going to check them off as I select them. So I'm going to select edge AD, which has the weight of 2. All right, it has the least weight. Remember in the algorithm here, it states that you pick the edge with the smallest weight first, all right, or the cheapest. Hence the cheapest link algorithm. Link meaning edge. Okay. So I'm going to select the edge with weight 2. I'm going to check it off. Okay, I've used that. All right, and then I go to my next edge, which is weight 3, and I select that one. And every time you select an edge, you have to make sure that you don't create a circuit early and you don't have any vertices of degree greater than 2. All right, and obviously with 2 edges selected, that's either one is not violated, so we're good here. Okay, what happens is that after the third edge is selected, or when the third edge is selected, that's when you got to start worrying about your 2 constraints. Okay, you got to have a circuit with all 5 vertices. Okay, so you don't want to create a circuit early and no degree 3 vertices. Okay, also notice here, and this is a little bit different than the nearest neighbor algorithm, is that the links or the edges that we just selected already, they're not attached, okay? They're not adjacent. Okay, that's not required in the cheapest link algorithm here. They do not have to be attached or connected by a common vertex. So they don't have to be adjacent. So you don't have to worry about that. You just select it anywhere in the graph. That's what I meant up here in the directions. I said select the edges anywhere in the graph. Okay. And step 2, pick the next cheapest edge anywhere in the graph. It does not have to be adjacent. In fact, let's write that down. Okay. Does not. I better spell that right. Okay. Does not have to be adjacent. Okay, so keep that in mind. Don't worry about that. Just go with the flow. When we're done with the circuit, they'll all be adjacent. Okay, that will happen automatically. Now, the next one here, weight 4. Let's select it here. If I select it, we cannot create a circuit early, and we do not want degree 3 vertices. Okay, and notice that C is degree 2. Look in red, not in the normal color here, not in black. A degree is only, B is degree 1, E is degree 1 so far, A is 1, D is 1, so we're good. All right, no circuits, no degree 3 vertices, so we'll check that off. Okay, now let's find weight 5, okay? Now weight 5 would be EB. Now watch what happens here. If I select EB, I got a problem, okay? Don't draw this, just watch here. Okay, notice that I have a circuit, EBC, only containing 3 vertices. Okay, it's a triangle. That's not good. You want a circuit with all 5 vertices, not 3. So we can't select that. So I'm gonna cross this one out. We cannot select this edge with weight 5 because it will create a circuit early. Okay, and then let's see here. So we can't select that. No circuit. Okay, can't create a circuit early. Let me write that down. So cannot create a circuit early. That's the reason why I can't select this one right here with weight 5. So let's go to weight 7. Okay, this happens to be edge AB right here. All right, and notice that B is degree 2, A is degree 2, and there are no circuits formed. So we can select that one here. How about weight 8? Okay, so where's the, okay, now this edge right here with that's weighted 8 right here. If I select it, we got a problem here, okay? Notice that if I select it here, C is degree 3 now. All right, that violates one of the constraints. Okay, so I cannot select edge DC with weight 8 because we have a degree 3 vertex now. So we cross this one out. Okay, so then you select 9. Okay, weight 9. Now weight 9 is right here. That's edge DB, and I got the same problem. B will have degree 3, and therefore cannot be selected. So 9 cannot be selected. All right, so cross that one out there. So we move on to edge weight 10. Now weight 10 here is edge EA. I got a problem there too because now A is degree 3. So don't select that one either. So let's select weight 11, all right, which happens to be ED. And notice that we finished the circuit, okay, or we completed the circuit. All right, so we have a circuit now which involves all 5 vertices, which is this is what we wanted. All right, and what we're going to do now is we're going to write the resulting circuit, the resulting one, starting at A. So here we go. All right, so let's see here. Start here. All right, let's say we go A to B, A to B to C, over here to E to D. All right, and then over to D, and then back up to A. Okay, so what would the weights be? So 2 plus 3 plus 4. No. I was reading my list here. I'm going to do it according to the circuit I wrote. Okay, so here we go. 7 plus 3. So 7 plus 3 plus 4 plus 11. And then back up to A, so plus 2 more. All right, if you add up those, let me see, you got 10 and 14, 25, 27. Okay, so you got a total weight of 27. Okay, now that was fairly easy to do, right? Okay, not that hard. Okay, you just pick the edges from smallest to biggest and make sure that you do not create circuits early and you do not have degree 3 vertices. Okay, that's all you do. All right, so one little note though, okay, before we try another one, is that this solution may not be optimal, okay, the least total weight, but it's at least a good approximation. All right, so let me just note that so you guys remember that. So this solution, okay, I'm talking about right here, may not be optimal. All right, and what I mean by that is the least total weight. Okay, all right, but it is a good approximation. All right, and that right there, my friends, is an example of how to find a Hamilton circuit using what's called a cheapest link algorithm. All right, you just got to get used to that, practice all the different forms, and get good. Okay, so example number 2 goes like this. I'll go over it in just a minute. Okay, I'm back, and so here we go. We're going to be a traveling salesman here, and we need to visit 4 cities. We need to organize a round trip. Okay, round trip. Ooh, that means a Hamilton circuit. Okay, that starts and ends at home, and that will pass through each city exactly once. That implies that we need to find a Hamilton circuit. All right, using the cheapest link algorithm. So here, keep in mind that we're using this new algorithm. Okay, not nearest neighbor, not brute force. All right. We are going to use the cheapest link. So here we go. We're going to select the edges as we go from smallest to biggest, and we're going to highlight as we go. highlight in red as you select them. All right, why? Because it makes it easier to see, right? Okay, so here we go. We got to compare, find the smallest one. 133, 119, 121. Ooh, it kind of looks like 119. Okay, so I'm going to select edge AC. Now, keep in mind, we're going to select edges from smallest to biggest. And we cannot create circuits early, and we cannot have degree 3 vertices. Okay, so what is my next one here? So the next one, the next cheapest edge would be this 120, right? Right after 119 is 120. That's edge EC. So I'm going to select EC. Okay, so we have that there. So we got two edges selected here. Now, my next edge here that's greater than, or the next cheapest edge, would be 121. However, I can't select this, all right, because it would create a degree 3 vertex at C. All right, so I'm going to cross this one out. So my next one after 121 is 133. It looks like here. Let's compare all these numbers here. But if I select this one here, I'm going to do it, okay, just for funsies right now. Notice that I create a circuit early. All right, that violates the two conditions, right? No degree 3 vertices, no circuits early. So I'm going to erase that. All right, so cross that one out. Can't select that edge. All right, and then the next one after 133 is, well, it's 150, right? Now 150. Now notice it's not adjacent to either one of the other two, but that's okay, as I was saying. So we're going to select 150. That's edge DB right here. All right, after 150 is 152 right here compared to 185 and 174. That seems like it's the cheapest. All right, I'm going to select that actually. Why? Because I'm going to select it. See if, okay, so go ahead and select that. Degree up here, A is degree 2, D is degree 2, C is degree 2. So far we're okay. No circuits, no degree 3 vertices. We're good so far. All right, the next one after 152. Where what it would be? Well, we're kind of we're forced with 200 here. Let me see. If I can't select 199 because that creates a degree 3 vertex here, so it can't do that. Actually, let me back up here. Okay, let's go in order. So after 152 is 174, right? Don't want to do that because that'd be a degree 3 vertex at D and at C. All right, 185, can't select AB either because we've got a degree 3 vertex at A. All right, so and then 199, can't select ED either because you got a once again another degree 3 vertex, so bad idea. And only that, using a little bit of common sense right now, we have to complete the circuit. So we're forced basically to select this one here, EB at weight 200. All right, notice we have a circuit now. So let's write the circuit starting at A. All right, so here we go. So we're going to start here. This is the start. All right, let's say that we go from A to C first. So this way, A to C at 119, and then over here to E. So cruise this way. All right, at 120. So A, C, E. All right, and then over here to B. And then to D here, and then back home, okay? D to back to A. So just follow the arrows, basically. Okay, so here we go. A, C, E, over here to B, D, and then back home. All right, so what are the weights? So we have 119 plus 120 plus 200 plus 150 plus 152. All right, and go ahead and add them up, and you'll see that you have a total cost of 741. Okay, Now, once again, we do not know if that's completely optimal, okay? But at least it gives us a solution fairly quickly, fairly easily, using what's called the cheapest link algorithm. All right? We'd have to write all the circuits out by brute force to see the optimal, okay? That would be the only way to produce that one here. And then we'd compare with the optimal to see how good we are. Okay, so now let's take a look at another example. Here we have a complete graph. Just notice that we have 1, 2, 3, 4, 5, 6, 7 vertices right here. And we have a table representing a complete graph with 7 vertices. And I say complete graph because none of the all the edges have a weight. Okay, so all the edges are there for 7 vertices, and they all have a weight. So we have a complete graph with 7 vertices: 1, 2, 3, 4, 5, 6, 7. And we want to find a Hamilton circuit starting at G when we're all done. Okay, so the way I usually do this is I plot the 5 vertices first, so in any order. So A is up here, B up here, C, D, E, and F. It doesn't matter where you place them, and then G right here, let's say. And then as I select them, I'm going to build the graph, and then what happens is that the Hamilton circuit emerges as you build it, and it helps you keep track of what you have in the graph. And it helps you also visualize whether you're forming a circuit early, okay, because we want a circuit not with 3 vertices or 4 vertices, but with all 7. And it also helps you visualize whether you have a degree 3 vertex or not. So if you do this at the same time, it kind of helps you out. So let's find the smallest weight in the graph. And by the way, on this right here, because there are no loops in the graph here, and is symmetrical here, you basically only have to look at the upper half. So let's not look down here. Let's just look at the upper half only. Okay, because it's symmetrical. All right, so eyes up here. So here we go. Let's find this smallest weight. Okay, and the smallest weight, I see is let me see, 20. Is there anything less than 20? I don't think so. Oh, 15. How about 15? Anything less than 13? Ah, here we go. So 13 looks like it's the smallest weight. So that happens to be edge FG. Okay, FG at 13. So let's go ahead and draw that. Let's draw as we go here. We'll have a little bit of fun. FG is weight 13. And there we go, weight 13. And I'm going to circle the weights as I use them, and we're going to cross out the ones that we cannot use, okay? And then we'll keep on doing this. We'll keep on looking at the next cheapest edge or the next least weight, and then we'll build a graph and cross out the ones we cannot use based upon the 2 constraints. And then at the end, the circuit emerges. Okay, so here we go. The next one, bigger than 13. Well, it's probably 15. Okay, 15. So let's take a look at here. Now, 15 happens to be edge AF. Now, AF. So let's build that. Okay, let's select it and build it. So here we go. That's 15 right here. And let's proceed. Okay, so after 15, the only tricky part about this is just comparing all the values. So what's the next cheapest edge after 15? Well, let's see here. Is it 20? 20, anything less than 20, between 15 and 20 now? It looks like 20 is it right here. 28, 22, 60, 65, 35. Just compare them all. All right, so the next cheapest edge is 20. Now, it happens to be DE. So let's build that. Can we select DE? And the answer is yes, because it doesn't create a circuit early. All right. And there are no degree 3 vertices. So there's weight 20 right here. Notice that it's not attached, it's not adjacent to the other 2, and that's okay. Okay, it does not have to be adjacent like in the nearest neighbor algorithm. We just select it anywhere in the graph. Okay, as long as it doesn't create a circuit early, and as long as it doesn't create a degree 3 vertex, we're okay. All right, so after 20, what's the next one? Let's see here, 28. Anything less than 28? Okay, so 28 happens to be AD. All right, so AD. Okay, select AD. Can we do that? Degree 2, all degree 2, no degree 3 vertices. All right, no circuits yet, so we can select edge AD, no problem. All right, so after 28 is 29, and here's 29. Now, can we select 29? Now, 29 is DG. All right, now DG would make, if I select it, now watch this. Okay, don't do this, but just watch, because I can change it real quick. That would make D degree 3, and that's a problem. Hamilton circuits, all the vertices are degree 2, not degree 3. So we cannot select DG. So I'm going to erase that. All right, and we cannot select DG, so we're going to cross this one out. All right, no degree 3 vertices. So the next one is 30, right? So here's 30 right here. 30 is BC. And BC, well, let's see here. Let me build that edge. Let's see if we can select it. Now BC is right here. And notice that we can select that one at 30 because we have not created a circuit early and we don't have any degree 3 vertices. So that one's okay. All right, after, oh, there's another 30 here. Okay, so 30 is FD. So FD, FD right here, that would make F. If I attach F to D, that would make F degree 3. So that is not allowed. So I'm going to cross out that one there. Okay, after 30 is 31. There are no 31s. How about 32? 32 is EG. Okay, now if I connect EG, did I miss one here? 32, 30, 20. Oh, I missed the 22 AG. I missed 22, so, and I missed 28. What? I missed, oh, there are two 28s. Let me go back. See, this is the only hard part about an algorithm because, obviously I missed the 22 and the 28. 22 here, AG, back here, AG. That would be a problem too because I would create a circuit and a degree 3, so 22 cannot be selected. 28, CG, CG. Okay, so before, let me go back here. CG could have been selected here because that right there, that would be okay. So CG, that we could select. So I made a mistake. I should have hit CG first or selected CG first with 28. I missed that one here. That would be okay right there at 28. Because that would be, well, that C would be degree 2. There are no circuits. This is 15 right here. All right. Apologize for that. So let me see. So 28. So 32. So 32. Can we select EG? And the answer is no. Okay, at this point, because now I made my correction right there. Sorry about that. I can't select EG because that would create G of degree 3. All right, so that wouldn't be any good. So I'm not gonna select EG, so I'm gonna cross that one out. So after 32 is 33s. I don't see any 33s, 34s. How about 35? Okay, I see two 35s. Okay, so how about this one, AE? Well, AE you can't select because A would be degree 3. And CF can't select that because I had two problems. Both C and F would be degree 3. So that's no good either, okay? So 35, 36, 37, 38, 39, okay, 40, 40. Okay, so can we select 40? Let me see. 40 is CD. Now CD can't select that either because both would be degree 3. So 40 is no good. And there's another 40 here, so EF. EF can't select that either. E's okay, but F's not. F would be degree 3. So can't select 40 either. So how about Oh, let me see. I got 50s. I got two 50s. AC, no good. A would be degree 3. And then BG. BG would not be good either because G would be uh, degree 3. So I only have a few edges. Oh, I've missed 48. So C, CE. Shouldn't be doing this at 7:50 in the morning. It's too early. So CE is 48. So 48 CE. CE is not possible either. C would be degree 3. No good there. So the only ones I have are, let me see, 60, 65, 75, and 80. So 60, let's try BD. So BD, no good. D would be degree 3. 65, that'd be BF, no good. F would be degree 3. 75, that'd be AB, no good. A would be degree 3. And so BE, okay, that is our only one left. And guess what? That completes the circuit. That connects all the vertices um, exactly once and forming what's called a Hamilton circuit. So this is weight 80 right here. So the only hard part, as illustrated by me, is missing a weight, okay, as you go from smallest to largest. That is the only challenging part about this. And I gave you a good example of that because I missed one in the table. All right, so let's write the circuit starting at G. So we're going to start here. Okay, so let's suppose that I go this way right here, okay, at 28. So G to C. So G, C at 28 to C to B. And then, so this way, and then B to E, and then to D. All right, over there to A, and then to F. All right, and then back home to G. Okay, so what do we have here? So let's write out the weights. So starting at G, so 28, don't look here. 28 is GC, so 28 plus 30 plus 80 plus 20 plus 28 plus 15 plus 13. Okay, and if you add all those up, my friends, okay, you get 214 to be total. All right, and that, my friends, is using the cheapest link algorithm. So, okay, so the total weight here, we don't know if it's optimal, but we do know that we have a solution right now by what's called the cheapest link algorithm. All right, and we wrote the circuit starting at G. You can write the circuit starting at any vertex. It would all be the same weight. All right, but the directions asked us to start at a G. There we go. All right, and this one here, okay, the table here in example 3 is the same as the weighted graph in example 4, okay? And so on this one here, you could try it. Keep a track of all the different weights and be very, very careful here. And you'll find that you have the same circuit as in example 3. So this is the graph of the table in example 3. I'm just making note of that, and you could do this one on your own. It's going to have the same weight of 214. So this is the graph of the table in example 3. So after you try this, okay, and you should do this by graphically right here, because that's one of the basic skills, and go ahead and find the circuit, go ahead and add them up, and you should have the same result as we had in example 3, okay, at 214. I'm going to leave that one up to you. I'm going to go right to number 5. Okay, so here we go. We're given a graph here with 1, 2, 3, 4, 5 vertices. This complete graph with 5 vertices. And what we want to do is find a Hamilton circuit starting at B when we're done. Okay, so let's select our edges here first. Okay, So we're going to find our cheapest edge, which I look at 9. 9 is smaller than 12, 24, smaller than all these different weights. Okay, so we're going to select that edge, and we're going to keep on selecting the next weighted edge as long as we don't create a circuit early and we don't have degree 3 vertices. Okay, the next one after 9 is 10. Sorry about that. After 9 is 10, 11, 12. Ooh, I see a 12 right up here. We can select that right there, no problem, because we do not have any degree 3 vertices and we have not created a circuit early, okay, with less than 5 vertices. All right, and when the first two edges, that's not going to happen anyways. We're not going to violate any of those conditions. It's when you add the third edge that you really got to really start paying attention. Okay, so after 12 is 13, 14, 15, 16, 17. Oh, I see a 17. Okay, so I'm going to select edge EC at weight 17, and E is now degree 2, C is degree 2. All right, no circuits are formed, so we're good there. All right, after 17 comes 18, 19. Okay, so sorry about the interruptions there, guys. All right, because I'm doing this at school. All right, so now is the next weight after 17 is 19, and I have two 19s. I have edge AD, which I cannot select. I'm going to show you why. If I select it right now, notice that I created a circuit, E, A, C, D, back to A. No good. That's a circuit with 4 vertices, and I want a circuit with 5 vertices, so I can't select that. So I'm going to cross this one out here. No good. All right. And so I'm going to select the other weight of 19, EB or AB right here. And I could do that because I didn't form a circuit and I didn't form any vertices with degree greater than 2. Okay, no degree 3 vertices. So after 19 is 20, no 20s, 21. All right, 21, don't want to select that either because watch what, if I do that, E becomes degree 3. All right, no good. All right, so I'm going to clear this one out. After 21 is 22. There's no 22, 23, 24. Here's 24. Now, if I select that, if I select edge EB, E becomes degree 3. No good. All right, so I can't select this one here. 25, 26, 27. If I select 27, right here, notice that I have C at degree 3. It's a degree 3 vertex now. No good. So I'm going to take that back. Can't select that edge. And then after 27 comes 28, 29. Okay, if I select that, okay, I complete the circuit. All right. And so we have accomplished our goal. So the only thing we need to do now is go ahead and write the circuit starting at B. Okay, because that's what it is asked. Okay, and this is again the result created by cheapest link algorithm. So I'm going to go from B to D. So B to D, over here to C, up to E, and then E to A. All right, and then back to B. All right, what would the weight of that be? So 29 plus 9, so 29 plus 9 plus 17 plus EA, which is 12, plus, let me see, plus 19. All right, and if you add those up, my friends, you're going to get a total weight of 86. Okay, now this is the solution from what's called the cheapest link algorithm. Oops, not G, but K. How about that? All right, cheapest link. Right there, you choose the cheapest link anywhere in the graph, making sure that you don't form circuits early and no degree 3 vertices. All right. Now this may be not be optimal, okay, but it is a decent approximation, and that's what we're looking for. A quick, easy solution that we can get to solve the problem. Okay? Okay. This is Mr. Ainsworth. I will see you in my next lesson later on. Make yourself proud by doing the practice, okay, which is obviously After my next example here, I'm going to stop early here. You guys can try this one here, the example 6. I'll come around and I will check your work on that one. And obviously practice right here. Numbers 43, 44, and 45. And you can check my solutions when you come back to class or on my website. Okay? This is Mr. Ranger. I will see you in my next set of lessons later on. Oh, look at this. We're at the end of the chapter too. So make yourself proud. Do your homework here. Start your reviewing process because we are going to test pretty soon. All right. I'll see you later. Bye bye.